Hello, good morning everybody. My name is Patali Kusuma Priya and I'm going to present a topic called 2D transformations, geometric transformations. What is a transformation? The geometrical changes of an object from a current state to the modified state is called a 2D transformation. Why do we need this transformation? To manipulate the initially created object and to display the modified object without having to redraw it is the main purpose of this transformation. When a transformation takes place on a 2D plane, it is called a 2D transformation. This plays an important role in computer graphics to reposition the graphics on the screen and change their sizes or orientation. There are many types of transformations, particularly the important ones are translation, scaling, rotation, shearing, etc. Some graphics are turned into something else by applying these types of rules on the particular image on the screen. Let us first talk about the translation. Translation moves or parallel shifts an object from one position to another position on the display. In other words, it is the shifting of a point to some other point whose distance with regard to present point is known. There is a simple operation that is easy to formulate mathematically. We want to move a point P1 to a new position P2. Let's say P1 has coordinates 3 and 5 and it is to be moved to P2 that has coordinates 8, 5. We see that they constitute a formulate an equation which is x2 equal to x1 plus something and y2 equal to y1 plus something, and this means translation is defined by adding an offset in x and y directions. Also, we can move the whole figure by moving all single points. For a many-sided figure, when a polygon is considered, we move all the corners. Let us see what scaling is. To change the size of an object, scaling transformation is used. In scaling process, we either expand or compress the dimensions of the object. Scaling can be achieved by multiplying the original coordinates of object with the scaling factor to get a desired result. We consider a single point as a starting point. Let's say P1 is same as x and y. We scale this point by multiplying with scaling factor of some value in both x and y directions. Therefore, we get a new point P2. The relation says that x2 equals x1 into xsx and y2 equal to y1 into sy. It is also strange to note that a scaling is considered just for a point. Therefore, we say vectors are scaled. We have different types of scaling. They are uniform and non-uniform scaling. What is a uniform scaling? It is basically a linear transformation that enlarges or shrinks objects by a scale factor that is same in all directions. The result of uniform scaling is similar to original. It is used to create a scale model of building, car, airplanes, etc. And the non-uniform scaling is obtained when at least one of the scaling factors is different from others. A special case is directional scaling or stretching in one direction. It completely changes the size of an object. For example, a square may change into a rectangle or into a parallelogram. If the sides of the square are not parallel to scaling axis, then the angles between the lines parallel to the axis are preserved, but not all angles. Usually when scale factor is larger than 1, it is called enlargement scaling, and when scale factor is below 1, scaling is called contraction. Now here comes an important type of a transformation called rotation. We take the help of rotation. Rotation, as the name suggests, is to rotate a point about an axis. This axis can be any of the coordinates or simply any other specified line also. The points of the body travel in circular trajectories around a fixed point called the center of the rotation. Can be a planar figure around a point is a movement of example can be a planar figure around a point is a movement of propeller of an aircraft. So the rotation can be better explained when we consider this following figure. We take the help of trigonometry in order to determine the rotation of an object. It is a little complicated over the other types of the transformations. In rotation, we rotate the object at particular angle theta from its origin. If a point P x comma y is at an angle phi from the horizontal x coordinate with the distance r from origin, let us suppose it has to be rotated to an angle theta. The resultant point is P dash, which has the coordinates x dash and y dash obtained, and this is obtained. If it is mathematically derived as, and we get the final point after the rotation as P2 involving the coordinates with certain angles of theta. Mathematically, it gives out a point P2 which consists of some kind sine and cosine values in its coordinate points. Now let us look at the mathematical matrix notations of this types of transformations. We want to find a common way to represent the operations. We know through linear algebra we can represent linear dependencies like these with matrices. In 2D transformation, we see that there is always representation done through 2 by 2 transformation matrix. Translation decided by t x comma y and scaling by sx and sy. For rotation, we do it through v, and it is one of the standard ways in which transformations are stored and performed in computer graphics. Now here comes the homogeneous coordinate system. The discussed three operations have a little different forms. We want the same form and thus introduce homogeneous coordinates. In general, why you want to perform a complex transformation, you usually make it by combining a number of basic transformations. In order to represent all transformations in same form, computer scientists have devised what are called homogeneous coordinates. These are simply a mathematical trick to make the representation be more consistent and easier to use. We also see a pictorial representation of the graph which represents the homogeneous coordinates. The 2D transformation for homogeneous coordinates. Here we add an extra virtual dimension. Thus, 2D transformations are actually 3D, and 3D homogeneous coordinates are actually 4D, and so on. When considered a 2D point P x comma y, we represent P as P x y and 1 in the matrix form. An extra coordinate is added whose value is always 1. It allows us to now represent translations as matrix multiplications instead of as vector addition. A translation is written as the following matrix, and scaling about a fixed point as simply a matrix multiplication. The matrix for rotation is also described in this slide. Inverse transformation matrix. The inverse transformation is found by taking the inverse of transformation matrix. Therefore, it is a transformation matrix T maps the point of coordinate systems. Then T inverse, that is the inverse transformation, maps the points from coordinate systems in a reverse fashion, that is from the second matrix to the first matrix. Naturally, it is one that applies the transformation T to a set of points and subsequently the transformation T inverse, then the points will not change positions and orientations, as T and T inverse when multiplied gives 1, that is identity matrix. Therefore the inverse translation matrix is shown for different types of the transformations we detailed. They are scaling matrix and rotation matrix and translation matrix, which are inversed. Now we see a comparison between the Euclidean coordinates and homogeneous coordinates. It is a mathematical system attributed by Euclid. It pretty much says that one line may be drawn through a given point parallel to given line. This geometry describes the shape as they are, where in a homogeneous the objects are described as they appear. Few properties of Euclidean coordinate systems such as length, angle and parallelism remain unchanged. In homogeneous coordinate system, the length, angle and parallelism become distorted when we look at objects. Mathematical models for how images of the 3D world are formed here. Let us look at the graphical interpretation of a 2D transformation. In 2D, the graphical orientation is done in a usual way of orienting the axis with positive x-axis point right and positive y-axis point up. It is also called a right-handed orientation. When two equations are considered, they intersect on graph except when they are parallel equations. Therefore, only one solution is obtained. Composite 2D transformations. When a transformation of a plane T1 is followed by transformation T2, then the result itself may be represented by a single transformation T, which is the composition of T1 and T2 taken in that order. It can be achieved by concatenation of transformation matrices to obtain a combined transformation matrix. The combination of various types of transformations such as translation, scaling, shearing, rotation and reflection results in composite 2D transformation. The changes in the order of the matrix transformation would lead to different results, as general matrix multiplication is not cumulative, that is A into B is never equal to B into A, that is associative property commutative property doesn't hold good, and the order of the multiplication too. The basic purpose of composing transformation is to gain efficiency by applying a single composed transformation to a point rather than applying a series of transformations one after another. For example, to rotate an object about an arbitrary point, we have to carry out 3 steps, that is, translate point x, y to 0, 0, that is origin, rotate it about the origin, and then the last step is translate the center of the rotation back where it belonged. Composition of the transformation is not commutative, that is what we proved. It is to note that composition of transformation is read from left to right. The result is not same as receiving from right to left. The order of the composite transformation is shown here, and then it is rotated, and in the first figure it is rotated about the axis and translation is done, and the other one is the translation which is followed by the rotation. Here Here we first translate the coordinates and then rotate it by an angle of theta. After the rotation, we translate it back. The matrix representation here clearly proves that. Reflection, it is the mirror image of the original image. Reflection is a special case of rotation of 180 degrees about a line in x and y planes passing through their origin. If two pure reflections about a line passing through origin are applied successively, the result is a pure rotation. The determinant of a pure reflection matrix is -1. We first translate followed by rotate, reflect, rotate, and then translate it back. The composition of two rotations from the same center is a rotation whose degree of rotation equals the sum of the degree rotations of initial rotation. Two initial rotations. In n-dimensional space, uniform scaling by a factor v is accomplished by scalar multiplication with v, that is, multiplying each coordinate of each point by v. Non-uniform scaling is accomplished by multiplication with any symmetry matrix. The eigenvalues of the matrix are the scale factors, and the corresponding eigenvalues are the axis along which each scale factor applies. A special case is a diagonal matrix with arbitrary numbers along the diagonal. In uniform scaling with a non-zero scale factor, all non-zero vectors retain their direction, or all have the direction reversed depending on the sign of the scaling factor. In non-uniform scaling, only the vectors that belong to an eigenspace will retain their direction. A vector that is sum of two or more non-zero vectors belonging to different eigenspaces will be titled towards the eigenspaces with large eigenvalues. Here is an example for the scaling about with respect to the arbitrary points. Rigid motion. What is rigid motion? Rigid motion is any transformation as a translation or rotation of a set such that the distance between points is preserved. There are 4 types of rigid motions. They are translation, reflection, rotation, and glide reflection. Translation. A translation is a transformation that slides each point of a figure the same distance in the same direction. The line connecting each point of the pre-image is its image as the lines connecting each point of the pre-image is its image are congruent. Rotation. Rotation about a point. A transformation in which a figure is turned about a fixed point called the center of the rotation describes the rotation in the rigid motions. Reflection. Reflection in a line. A transformation that uses a line that acts like a mirror called the line of reflection with an image reflected in the line. Since all points move across the line of reflection, the image of each point will be the same distance away from the lines as the pre-image. The glide reflection is a mirror reflection followed by the translation parallel to the image of the mirror image. Every glide reflection has a mirror line and the translation distance. reflection properties. If two pure reflections about, as mentioned before, if two pure reflections about a line passing through the origin are applied successively, the result is a pure rotation. The determinant of a pure reflection matrix, as discussed before, is -1. Now, coming to the reflections with respect to the arbitrary lines, when we consider a line y equal to mx plus c, where c is the y-intercept, can be accomplished with a combination of translate, rotate, and reflection transformations. The steps involving the series of reflections with respect to the arbitrary line are in a process, and it is represented in a flow chart. That is, translate the working coordinate systems so that the line passes through the origin, and then rotate the working coordinate system such that one of the coordinate axis lies onto the line, and then reflect about the aligned axis, and restore the working coordinate system by using the inverse rotation and translation transformation. Now, reflection with respect to x and y axes can be represented in the form of a matrix, and they are given below. It is seen that they are -1 0 0 -1 for x-axis and -1 0 0 1 for y-axis. Shear transformations produce a shear distortions. In 2D, the shear is x and y directions, which converts a rectangle into a parallelogram. In plane geometry, a shear mapping is a linear map that displaces each point in fixed direction by an amount proportional to its signal distance from a line that is parallel to that direction. This type of mapping is also called shear transformations, transfections, or just shearing. Shear mapping must not be confused with rotations. Applying a shear map to a set of points of a plane will change all angles between them, and the length of any line segment that is not parallel to the direction of displacement. Therefore, it is usually distinguished in the form of geometric figures. For example, turning squares into non-square parallelograms, as discussed in the slide, or turning a rectangle into the parallelogram. And an example with the matrix representation is also shown. Raster methods. Rasterization is the task of taking an image described in the vector graphics format and converting it into the raster image for output on a video display or printer, or for storage in a bitmap file format. It refers to both rasterization of models and 2D rendering primitives such as polygons, line segments, etc. The normal usage, the term refers to the popular rendering algorithm for displaying 3D models on the computers. Compared with other rendering techniques such as ray tracing, rasterization is extremely fast. However, rasterization is simply the process of computing the mapping from scene geometry to pixels and does not prescribe a particular way to compute the color of those pixels. Shading, including programming shading, may be based on physical light transport or artistic intent. A translation and raster methods takes place in a series of steps where copying a block from one area to the other area of the frame buffer and fill the old area with background color and begin with an overlapped corner. The rotation in raster methods is described through the following figure. And rotate a two-dimensional object or pattern 90 degrees counterclockwise by reversing the pixel values in each row of the array, then interchanging the rows and the columns. And this is the rotation by shear, where a source is turned first into shear up and down, and then in all directions in the other directions, where the final shear image 3 is different from the source and it is turned into a parallelogram from a square. The 3D transformations. Geometric transformations are mapping from one coordinate systems onto itself. The geometric model undergoes changes relative to its model coordinate systems. The transformations are applied to an object represented by point sets. We see the rigid body motion, which is called the relative distance between the object particles remaining constant, and the transformed point set is shown with the help of transformation parameters. 3D translation is from a point P with coordinates x and y is translated to P dash by T, that is the transpose. That is the translation. Below matrix is the translation matrix. 3D reflections. We can also perform 3D transformations about a plane now. Rotation of 180 degrees about an axis passing through the origin out into 4D space and projection back onto 3D space. Through x and y planes, we see the matrix of the rotation given below, and the YZ and XZ planes has the matrices shown here. And remember that the determinant of the t is -1. 3D rotation. It is more complicated than 2D rotation since we must specify an axis of rotation. 3D, the axis of rotation can have any spatial rotation. That is, the z-axis rotation is in the anti-clockwise towards z direction, and in y-axis rotation is anti-clockwise towards in x direction, and x-axis rotation is in anti-clockwise direction towards y rotation. And the matrices notations for these x, y, z axes are also given. 3D reflection. A reflection through the xy plane is represented in a standard form of a matrix, which is represented here. Reflection through the xz and the yz planes are defined similarly. Transformation between 3D coordinate systems. The coordinate systems has a set of points that are the old coordinate systems to the new coordinate systems over it. We need to do the transformation, which involves translation as well as the rotation. The figures for the transformation between the 3D coordinate systems are shown below. The method of orthogonal vectors. In mathematics, two vectors are set to orthogonal if they are perpendicular to each other, that is, they form a right angle. They also satisfy the symmetric property where x is orthogonal to y and y is orthogonal to x.